right, to wrap up this very long chapter, I'm going to go ahead and skip to a few slides, skip through a few slides, and go to this one here. Color is a construction of the nervous system. So our receptors in our eyes are perceiving these waves of electromagnetic energy coming at us at different frequencies. Those waves themselves have no color. Color is a construction that we make as a result of that stimulus. The waves are simple. Light waves are simply light waves. They don't have any look associated with them. Even Isaac Newton knew that when he was doing his theories of optics back in the 1600s. So the colors that we perceive are constructed by our central nervous system. We really don't know how other critters perceive colors in their world. For example, honeybees. Honeybees perceive ultraviolet light. They do not. They do see some in our color spectrum, but their perception is actually most of what they can perceive is in the ultraviolet range. We really don't know what that looks like. We can't. There's no possible way for us to say what color the bee is quote seeing, only because their nervous systems are constructed to enable that perception in such a way that we can't get into it and understand it. The visible spectrum of light, which you can see here, those colors that we perceive go away in very low intensities. So if I were to have this spectrum printed out on a very nice card and then show it to you in very low light that you've become acclimated to, you would have a tough time making out these colors. As a matter of fact, it would look pretty gray to you for the most part. You might see a little bit of blue here toward the bottom, but for the most part, you'll just see sort of these shades of gray in very, very low light. Does that mean the colors are gone? Does that mean that they somehow got converted? Well, no, because we still have the same pigments here. And whenever the proper amount of light hits them, they will reflect off. They will absorb and reflect the way they're supposed to. But just because it looks different to us in different intensities of light doesn't mean that there's been some physical change here with the pigments or with the wavelengths. They're still there with the proper amount of light. It's just that our brain is constructing a different reality for us based on the amount of illumination and intensity of light that we have. This chart here shows the absorption spectra for bee eye pigments. So of course, bees have little, eyes right in the front of their little heads, and they actually are fairly visually oriented, very visually oriented, in fact. That's why flowers look the way they do. That's why we have so many different colors of flowers, because flowers are trying to attract bees with bright colors. So the bees go and they see these bright colors in ultraviolet, and they go and they pollinate those particular plants. But you'll notice that most of the visual pigments are in the very ultraviolet wavelengths here, 3 to 400. If you remember, we only see from about from here to here, I guess. But bees can see in the very deep ultraviolet from 300 nanometers to 450 nanometers. This is true for all of the energies that we perceive, not just for vision. So, sound, for example, we perceive sound. And the sounds that we perceive are based upon the changes in waves that travel through the air, sound pressure waves that travel through the air. So we can actually take a picture of these sound pressure waves, and the ones that produce a very low sound are more farther spaced than the sound waves that produce a very high sound. But do these Does this physical movement of energy through air have a pitch? No. It does not have a pitch or a sound associated with it. It's not uh, the pitch that you hear, whether it's a high pitch or low pitch, is not at all a particular property, physical property of that energy. The pitch that we perceive is simply what our brain is constructing for us based on how that energy is vibrating the mechanism of your inner ear. Taste is the same way. This molecule here is quinine or quinine. Quinine has a very bitter taste to it. It's one of the most bitter substances we know. And this particular molecule here is sucrose, which of course is sugar, and it has a very sweet taste. There's nothing about these molecules that inherently has bitter and sweet associated with them. It's just we perceive molecules with this particular grouping carbohydrates. We perceive these as being sweet, and we perceive these types of molecules with the rings as being bitter. And it's simply a result of our evolutionary history, and goes back to why we need to perceive certain things as sweet and certain things as bitter. But there's nothing in the molecule that is bitter or sweet. It's just that's the construction that our brain makes when this substance hits our tongue or when this substance hits our tongue. One way to understand how it is that vision develops is to look at what babies can see. And that's a really tough problem. It's a very tough problem to try to understand what it is that infants see. Uh, Especially like very young infants, like a newborn, like a baby that's about a month old. We can only imagine. Um, they do have color vision. But how exactly they perceive chromatic colors, we're figuring out. How do they perceive brightness, right? They can do this, and you can actually measure what infants can perceive and not perceive by using a procedure known as habituation. So babies, even very young babies that are like a month old, will look at something that's fairly close, maybe a foot or so in front of them. They will look at something that is new to them. If they've never seen it before, they will look at it and they'll process it. And you can actually measure how long they spend looking at something by measuring how long they turn their little heads and look at it. After they've gotten bored with it or they've gotten habituated to it, they'll quit looking at it. So you can measure actually how interested they are in something uh, um, by measuring how long it takes for them to get habituated to it. And what we presume is that since they're looking at it, they must be able to perceive it in order to be able to look at it and be able to have interest in it, and eventually, of course, be able to habituate to it. From doing these types of studies with habituation, we know, for example, that infants do have color vision. They will look at new colors that are presented to them and habituate to them after a while. So if you show the babies a red square uh, for a while, and then they'll get bored with it and they'll look away to something at another square. Then you show them a green picture or a green circle or another green square. They'll look at that for a while, and then they'll get bored with it and look away. Then if you show them the red square again, they'll look at it, but they won't spend as much time looking at it. They'll look at it and go, "Oh, I've seen that before," right? So in that way, you can tell what it is they're perceiving and what it is they're not perceiving. Um, this is an interesting demonstration here. Here we have a yellow square and a red square, and the same two squares are in B, except we ran them through a photocopier. So you took a black and white photocopier and ran them through. And you've all done this, right? You've all run color images through a photocopier. One of the things that you'll notice is that the photocopier is able to tell the difference between the two squares, or at least the image that it produces looks different, in that the red square looks darker than the yellow square. So what that tells us is whenever we're trying to study color perception, we have to take into account not only the different colors, but how bright they are. In this example here, the yellow color is brighter than the red color. The red color is darker than the yellow. And we see that clearly in the black and white image. So if you wanted to use these two colors as a stimuli, one of the things you'd have to do is to make either the yellow darker or the red lighter. You'd have to adjust the intensity so that they're the same. That way you're purely looking at the color of the stimulus and not confounding that study with intensity or brightness.